Okay, continuing on with our lesson 1.4, limits and continuity. We last left off class with just looking at piecewise functions and how piecewise functions are going to be functions that we will often see here in calculus. So when they come up, they'll come up and we'll talk about them then. But let's move on to investigation number B. What is the relationship between limits, continuity, and discontinuity? So examine graph A. Is it continuous or discontinuous? So as I look at graph A, if I trace graph A, you'll see that I can just trace it without lifting my pen. And when you can do that, then you know it is continuous. Right? So it can be drawn without lifting your pen. In part B, determine each of the following for graph A. Can we find the limit as x approaches neg 2 to the left of f of x? So if 2 is here, and then the limit as we approach 2 from the left side is going to be a y value of 3. If I look at the limit as x approaches 2 from the right side, I'll look at approaching 2 from the right side, and that limit is also approaching 3. And so if the left-hand limit, the left side limit is equal to the right-hand limit, or the right side limit, that would mean that the limit as x approaches 2 of f of x is equal to 3. Okay, and also if I evaluate f of 2, there's that point right there, that is also 3. Okay, so what do we notice when we compare all of these values? Well, we notice that they are all the same. And how do the values we found in part B support our answer in part A? Well, going to the definition of continuity, the definition of continuity states that f of A has to be defined. The limit as x approaches a of f of x exists, which it does, and that the limit is equal to f of A, and that's what we have here. So the limit as x approaches 2 is 3, as well as the defined value is equal to 3, and so it passes the definition of continuity. So it passes the definition of continuity, meaning it meets all the criteria. Okay, let's look at number 2. Examine the graph B to the right. Is it continuous or discontinuous? This time, as I trace my graph, I'll reach a point where I gotta lift my pen and then move and finish the graph. So that is a function that is discontinuous. So discontinuous. Why? Because there is a break in the graph. Okay, then let's look at some of the limits here. The limit as x approaches 2 from the left. This time we're approaching that y value of 3, so we're going to say 3. Let's look at the limit as x approaches 2 from the right. So up here it looks like it's approaching a y value of 4. So therefore, if the left-hand limit and the right-hand limit are not the same, right, the left-hand limit's not equal to the right-hand limit, that means the limit as x approaches 2 does not exist. Okay, g of 2, can I evaluate g of 2? And certainly can. That is the filled in point, not the hollow point, so the filled in point there is equal to 3. Okay, so what do we notice? The values here are not equal. Okay, there's no limit that exists, and the left-hand limit is not the same as the right-hand limit. So since the limit as x approaches 3 does not exist, then f of x is not continuous. Okay, so that's part B. Let's look at the third question here. So let's examine a third graph, graph C. Is this one continuous? Well, as we can see here that there are more breaks in this graph, we are going to say it is discontinuous. Okay, and again, I cannot draw this graph with just one stroke of a pencil or a pen. There are breaks in between. And I can evaluate some limits. So let's look at the first limit. The limit as x approaches 2 from the left. 2 from the left approaches the y value of 3. If I look at the limit as x approaches 2 from the right, it looks like it's approaching a y value of 4. So that means, again, the limit does not exist because the left side is not equal to the right side limit. Okay, h of 2, okay, if I look at where 2 is and the y value is defined by that filled in solid point, not the hollow empty points, that solid point says my h of 2 value is equal to 6. Okay, so when I compare the values found, none of them are the same, nothing at all. Okay, and again, my answer here is none of these. My answer is the left-hand limit is not the same as the right-hand limit. The limit, the double-sided limit as x approaches 2 of h of x does not exist. So h of x is not continuous. Okay. All right. So we can, when we talk about a function being continuous, we mean that the graph passes through the point without any breaks. Okay. So a graph that is not continuous at a point, sometimes referred to being as discontinuous at a point, will have some kind of a break. Okay. And there are some graphs here that will illustrate what kind of breaks we can have, what kind of discontinuities can we have. Okay. So the first one is the case where it's continuous along its domain at every single point on its domain. Okay. So that's one case. In many cases will be like that. Okay. Here we have on the case part B is a discontinuity at x equals 1. So if I really zoom in here, here's a graph. How would I well, if you want to graph this yourself, the graph of this function, so this graph looks like it's a y-intercept of 0 with a slope of 3. So that looks like it's a graph of 3x, but you have a hole, and when you have a hole, that means you're going to have a rational function with a denominator of 0 somewhere, right? So this hole is at x equals 1. So if I had a factor of x minus 1, that means when x equals 1, the denominator is 0. So to have a hole, you have to have a x minus 1 on top. So for those who don't know where holes come from, I believe you may have studied them in grade 11. But remember, if you had indeterminate form, a 0 over 0, which is what you have here with x minus 1 over x minus 1, that is what produces holes in our graphs. Okay, so you can have a point discontinuity, which is a hole such as this. Okay, sometimes the points will be defined where you might have a removable discontinuity. That point could be defined somewhere else. Okay, so that also can happen, right? So you could have the hole, but also the function could still be defined somewhere else along there as well. So point discontinuity. Maybe you might hear the word removable discontinuity, which means there's removable discontinuity where the point is still defined, but somewhere else in the graph. Okay. Then we have a jump discontinuity like this at x equals 1, where your graph jumps from one part to reach the next part. And you can also have an infinite discontinuity with things like asymptotes, like a vertical asymptote. Okay. So those are the common discontinuities that we will encounter in our course. So let's look at the next question. Examine the graph. So let's look at this graph. So again, we have a piecewise function here. Okay, made of a function made out of 3 pieces. So the first part is 0.5x squared, which is our parabola. We could recognize that as a parabola. -2, which is a single point here because it's defined only at x equals 1. The parabola is defined when x is to the left of 1. And then we have a linear function with a negative slope when x is greater than 1 on the right side of 1. Okay, so what's the domain of our function? Well, it appears that every single x value is represented somewhere in this graph. So my domain is x is the element of all real numbers. Or if you're familiar with this notation, so we could say in -infinity to +infinity, or maybe you've seen this before, a -infinity less than x, which is less than +infinity. Okay, so multiple representations of our domain. Now, can I evaluate some limits? The limit as x approaches 1 from the right. So from the right, I'm going to be following the linear function, and that's approaching a y value of 2. It's not equal to 2 because there's no defined point there, but it's approaching 2. Okay. The limit as x approaches 1 from the left. So I'm going to follow my parabola, and that's approaching what looks like 0.5. But if we really wanted to be sure, then we could just, take that function 0.5 times x squared. If I plug in 1, yeah, then we know that's 0.5. Okay. And let's look at what's the limit as x approaches 1. So to know what that is, you have to look at the left-hand limit. All right, that's the 2, and the right-hand limit. Oh, my apologies. It's reverse right-hand limit, which is the 2, and then the left-hand limit, which is 0.5. We don't see that they're different. They're not the same. They're different. So if that's the case, then the limit as x approaches 1 does not exist. DNE. Okay. F of 1 is still defined as a solid point down there, and we see that is -2. So is the function discontinuous? Yes. By the definition of continuity, the limit does not exist. So the limit does not exist at x equals 1. So the function f of x is discontinuous. Okay. Continuity at a point. So the function f of x is continuous at x equals a if f of a is defined and if the limit as x approaches a is equal to f of a. So just a reminder again, what is that definition of continuity? So whenever you're asked is a function continuous, you must follow the definition of continuity. You must find the limit, the left-hand limit, the right-hand limit, the two-sided limit, and check if it's equal to the defined value of f of a. Okay, if it's not, then the function is discontinuous. Okay. All right. So before moving on, I'm just going to bring your attention to your textbook. There is a page in your textbook that I wanted to show you. It is limit properties. This would be on page 35 in your textbook. So there are a series of limit properties. Think of like algebraic properties, when you're the distributive associative laws and stuff like that. There are properties that help us solve for limits. So one of those properties is the limit as x approaches a of some constant c. So c is a constant. We're treating it as a constant, not a variable. A limit of a constant is just a constant, right? So think of a graph. Here's an x-axis. If I draw some y value, could be whatever, 2 maybe, 3, whatever. It's a constant linear line. No matter what value of a you have, you're approaching the left side and the right side of a. That's still going to be that constant value. Okay. If your limit's just a linear function x, as your x approaches a, your limit's going to be a. Okay. You have things like two functions. If you're adding two functions and you're finding the limit, you can split the functions separately and you can add their individual limits like that. If you're subtracting two functions and finding the limit, you can also do it separately by finding the limit of the first function and then finding the limit of the second function and then subtracting that. If you have a function with a constant in front of it, like it's 5x squared, for example. So 5 is a constant. I could take the constant out, 5, and then find the limit as x approaches a of x squared. Okay, so I can do that too. If I'm multiplying two functions and finding their limit, I could find the limit of each function first and then multiply your results. Okay, and the same thing for division. The limit of a function divided by another function is this equal to the limit of the function on the top divided by the limit on the function on the bottom, provided that your denominator is not 0, because you cannot divide by 0. And then finally, when it comes to powers, you can do the same. Similarly, you can have if a function raised to a power, and you're evaluating that limit, well, you can find the limit of the function and then raise the result to the power n. And in a similar notion, if power n was a fraction, a rational number, then you're really going to have a square root, right? So the limit as x approaches a of a square root of some polynomial inside the square root, you can change that and evaluate the polynomial, the radicand. You can evaluate the limit of the radicand and then take the nth root. Okay, so just some limit properties that may come in handy later on. Okay, so just some examples. The limit as x approaches -1 of a constant 5, well, that's just going to equal 5. Okay, the limit as x approaches 2, like you might be inclined to just do direct substitution, and that would be okay, but we can also evaluate the limit separately. So I can evaluate the limit as x approaches 2 of 3x to the power 4 minus the limit as x approaches 2 of 5x. And I can evaluate that and then get the same answer, right? So 3 times 2 to the 4 minus 5 times 2. Okay, and so that should be 2 to the power of 4 should be 16. 16 times 3 is 48. Minus 5 times 2 is 10, so that should be 38. Okay, and similarly, you can apply the rule for the square root, the f of x over g of x, two multiplying functions again, and same thing for that. And then I'll show you a couple more examples as I go back to the main notes. So I'm just going to switch back to the main notes page here. Okay, so evaluate each limit. So this was just some more of the same thing. We already did that one. That was 5. And then this one was 38, I believe. We got that one, 38. And so I'll do a couple more here. Same idea. I could evaluate the limit of the radicand as x approaches -3. So of the inside, 2x plus 5. And then take the square root of everything, right? So the limit of the radicand here is -3. So 2 times -3 plus 5. And that's equal to -6 plus 5, which is -1, and we can't evaluate the square root of -1, so the limit does not exist. And then we have the limit as x approaches 2 of 5x over x minus 2. So in most cases, I mean, you will probably just do direct substitution. So it'd be 5 times 2 divided by 2 minus 2, and well, what happens here? We have 10 over 0, and we can't divide by 0, so the limit does not exist. And in fact, if you looked at the left-hand limits and the right-hand limits, so if I look at x approaches 2 from the left, right? 2 from the left, meaning you're picking a number from the left, like 5 times 1.999 divided by 1.999 minus 2, you're going to just approach a extremely large negative number. And the same thing if I look at the limit from the right side of 2, I can say 5 times 2.0001 divided by 2.0001 minus 2. And as I increase the number of decimal places, you're going to get a very large positive number, right? So we'll represent very large numbers using the infinity symbol here. Okay. And so when you have a negative large number and a positive large number on the left and right side, then yes, your limit's not the same. Your left hand and your right hand limits are not the same, so it does not exist. Okay. Other strategies you may need to do to evaluate limits. So sometimes the main strategy is you try direct substitution first. Okay, so if I try direct substitution, the limit as x approaches 1, if if I tried direct substitution, I would get 1 squared minus 6 times 1 plus 5 for the numerator, divided by 1 squared minus 3 times 1 plus 2 for the denominator, and we'll discover that we have 1 minus 6 plus 5 on the top, and then 1 minus 3 plus 2 on the bottom. And the problem here is, although the numerator may the numerator will give you 0, and the denominator will also give you 0. The issue is the denominator. You can't really divide by 0, right? So what do I write for my answer here? So you're gonna get these situations where you're gonna end up with a 0, right? And you cannot just say there's no limit, okay? You're gonna have to try and find the limit as x approaches 1, and there are other strategies you can use to find that limit. So recognizing that what we have here are two quadratic polynomials on the top and the bottom, things you've learned in grade 10 and 11 are factoring. So if I tried factoring this, the limit as x approaches 1, okay, notice when I'm writing limits, you keep the limit notation because we haven't substituted 1 yet, right? So I'm going to keep the limit notation here. I'm going to write the factored form of the numerator. So two numbers that multiply to give you 5 and add up to -6. Well, those are going to be -5 and -1. So x minus 5 times x minus 1 divided by, let's factor the bottom. Two numbers that multiply to 2 and add up to -3. Well, those factors are going to be x minus 2 times x minus 1. Okay. Now I can try and evaluate this limit. And just before I do that, I'm going to just see that, hey, I got two factors that are the same here, in the top and the bottom, which allows me to cancel that, okay? So when I cancel that, I'm left with x minus 5 over x minus 2. So I'm going to be evaluating the limit as x approaches 1 of x minus 5 over x minus 2. And then again, I'm keeping the limit notation here. I'm keeping this limit notation because I haven't substituted x yet. But then now when I substitute this x, I don't need the limit notation anymore. I'm just going to write 1 minus 5 over 1 minus 2, and that equals -4 over -1, which is equal to 4. So my limit as x approaches the value of 1 is equal to +4. Okay, and you can graph this just to see for yourself that it is true. Okay, so what a difference it is from going from getting a 0 to actually getting the proper limit. So whenever you encounter a 0, like a division by 0 like that, or a 0 over 0, you're going to be looking at a different strategy to find the limit. So the strategy we used here, so the strategy here is to factor and simplify. Okay. Let's look at another question. The limit as x approaches 0 of 4 plus x minus 2 over x. If I substituted 0 here, you're probably going to right away see you have a problem, right? I can do 4 plus 0 minus 2 in the numerator, right? But x is already a 0 in the denominator, and you're still going to get a 0 over 0. So the problem is 0 in the denominator. Okay, so I can't use direct substitution for a question like this. So direct substitution does not work. So what's a strategy that we can try? Well, we have a square root here. This is not like a quadratic that we could factor, but we did go over conjugates. Okay, we did go over rationalizing, so we can rationalize the numerator. So the strategy here is rationalize numerator by multiplying by its conjugate. Okay, so what's the conjugate? So I'm going to write here the limit as x approaches 0 of the square root of 4 plus x minus 2 over x times the conjugate is going to be the square root of 4 plus x. The minus becomes a plus, and then I keep my 2. And the denominator, same thing, square root of 4 plus x, keep the plus, and then a 2. Okay, Then you multiply everything out. Remember the whole point of multiplying by conjugates is to get this whole, a squared minus b squared equals a plus b times a minus b, right? So if I have an a plus b and a minus b, so think of this as the a and the b, this is an a minus b and an a plus b, then I know my result is going to be a squared minus b squared. So the limit as x approaches 0 is going to be the square root of 4 plus x squared minus 2 squared, all divided by x times the square root of 4 plus x plus 2. Oh, I should put that in brackets like that. Okay. Now, are there things I can simplify? Like, absolutely, right? I can simplify this even further. So I'm going to have the limit as x approaches 0. 4 plus square root of 4 plus x squared. The square root and the squares cancel, so I have 4 plus x minus 2 squared, which is 4. So minus 4 divided by x. I'm going to leave the x as is, square root of 4 plus x. The reason why we don't expand the bottom is because we're looking to see if maybe we could simplify things first from the top. So it looks like I can, right? So I can go 4 minus 4, those cancel out with each other, right? And that leaves me with an x on the top, but I do have a factor of x on the bottom, so that will be the limit as x approaches 0 of x on the top divided by x times the square root of 4 plus x plus 2. And so my x terms can cancel from the top and the bottom, so that goes with that. And now I'm left with, I'm going to run out of space, limit as x approaches 0 of 1 on the top, right? So x divided by x is just 1. And on the bottom I have the square root of 4 plus x and then plus 2. So I've transformed the original question, this thing, okay, by multiplying by its conjugate to rationalize the numerator. So you see the numerator is now rationalized, okay? And then maybe now I can substitute the 0. So notice how I kept the limit notation all this time. Okay, you have to. That's proper notation. You have to keep that limit notation until you're ready to substitute 0. So I'm going to substitute 0 now. So 1 divided by the square root of 4 plus 0 and then plus 2. Okay, the square root of 4 plus 0 is 4. So the square root of 4 is 2. So that's going to be 1 over 2 plus 2. And that's equal to 1 over 4. Okay, and that is my limit, and that's the answer. Okay, so that is another strategy. So by far the most common strategies I am showing you here are to factor either you're going to be factoring and simplifying, or perhaps you'll be using conjugates. Okay, so we'll leave it at that, and that is the end of 1.4.